Hello, everyone. The work I am presenting today is entitled Sample Sharing and Prioritization in Multi-Agent Deep Reinforcement Learning, and this is joint work with Patrick Fabiani from Dassault Aviation. So this is going to be quite theoretical work, so maybe I can take just 1 minute to give a concrete example of an application of such work. So imagine a game with a red team and a blue team that are fighting against each other. And let's say that the blue team is prepared for fighting against the red team because it has learned some expected behavior from the red team. And the system is deployed, and the red team is not behaving as expected. So the blue team has to adapt and to adapt very quickly. And that's a very difficult problem to adapt very quickly. So this work is an attempt to bring some answers to this very difficult problem. So a few words. No problem. Thank you. Okay. So a few words about me. I'm a research engineer working at Dassault Aviation. So I've been working on reinforcement learning since 2020, and my past research focused on important sampling to speed up the learning curve of a deep RL algorithm using a replay buffer like the DQN algorithm. So past research work focused particularly on prioritized experience replay. If you're not familiar with prioritized experience replay, I will come back to it because it's a very important source of ideas for this work. And this is a work on multi-agent reinforcement learning. So the multi-agent reinforcement learning framework is built on Markov decision processes. So in the Markov decision process, we have a certain number of agents that are, and the environment that are interacting with an environment. The agents are in a certain state. They have some observations coming from the environment. Then they all take an action, and the concatenation of all actions makes the environment transitioning from one state to a new state. And now all agents receive a new observation from this new state and also a reward. And this process goes on and on until we meet a terminal condition or a goal state. And in this framework, we define an experience as a tuple made of an observation for agent I, the action of agent I, the new observation of agent I, and the reward received by agent I. So in this work, we're focusing on collaborative tasks and algorithms using a replay buffer. So maybe among deep RL algorithms using a replay buffer, the most popular one is the DQN algorithm, the deep Q network algorithm for discrete action spaces, and soft acrocritic for continuous action spaces. So the DQN algorithm, let's focus on it, is an algorithm made of a replay buffer that gathers all past encountered experiments collected by interacting with the environment, and a neural network who learns the expected behavior by sampling uniformly the replay buffer where everything can be found. So the idea of this work is to say, okay, we are working on a collaborative task. We have M agents, for example, and all agents have collected a certain number of experiences through the interactions with the environment. And the idea is to wonder, okay, how can we share efficiently experiences among agents so that learning is better? to learn better policies. So as multi-agent system is a very broad research area, let's focus a bit more on what we're working on. So we are considering M agents that have to collaborate on a certain task. And there are two important assumptions in this work. So the first important assumption is that we are dealing with homogeneous agents, which means that all agents have the same action space. And it is important because we are sharing, the goal is to share experiences among agents. So it would be a nonsense to share an experience with another agent that could not take the same action. And the other very important assumption is the environment being anonymous to all agents. So I'm not sure the term anonymous is really standard in the literature, but what it basically means is that the environment behaves the same way for all agents. So for example, if agent 1 takes action move north, and move north happens with probability 1, then it should be the same for all other agents. Because once again, we are sharing experiences. So if we are sharing the experiences containing observation, action, reward, and new observation, then the experience should reflect the same environment behavior for each agent. So in this kind of environment, it's necessary to identify the baselines multi-agent expert would immediately think of. So the first baseline is the parameter sharing baseline. So in the parameter sharing baseline, for example, let's focus on DQN being the base agent for our study. So the parameter sharing baseline, we have one neural network and one replay buffer where everything can be found. So we have multiple agents interacting with the environment, and they are gathering experiences, and they put it in the replay buffer, and the neural network sample this replay buffer to learn the good policies by sampling uniformly it. So this is an important baseline, and the other important baseline is the eye-dependent learning baseline. Here we are talking about the DQN agent. So let's continue with the DQN agent. So the independent DQN baseline, we have M neural networks. So we have M independent agents, M neural networks, M replay buffer, and each agent interacts with the environment and collects its own experiences and learns thanks to its own experiences. And no communication is allowed. So these are two very common baselines, and it is quite difficult to say which one is better in general between the parameter sharing baseline and the eye-dependent DQN baseline. But it's not the purpose of this study. The idea of this research work is to wonder if when you have a multi-agent system that is already deployed, already in production, and the environment is changing a bit. For example, you are the blue team and there is a red team, and the red team is changing its strategy. The question is, okay, how can you adapt to this new behavior? And if a small bandwidth of communication is allowed between blue agents, can you share interesting experiences between these agents so that learning become faster and to converge to a new good policy? So we proposed an algorithm named the large batch sharing algorithm. So the idea is that at each learning step, each agent samples a mini batch from its replay buffer. Then the mini batches are concatenated to form a large batch, and this large batch is shared among all agents. And each agent receives the large batch, and we compute on this large batch. So each agent computes on this large batch interesting quantities to download the large batch to a mini batch and to perform stochastic gradient descent on it. So the question is, obviously, how do we downsample the large batch to the mini batch. And that's where we go back to prioritize experience replay. So prioritize experience replay is an algorithm that has been built on top of DQN. It has been introduced in 2016 by DeepMind. And the idea is to associate a priority list to the replay buffer in the DQN algorithm, and to do the learning not via uniform sampling of the replay buffer, but a sampling prioritized on the priority list. And how do we compute the priority list? Well, in prioritized experience replay, the priorities are the temporal difference errors. So for those who are not familiar with the temporal difference errors, let's say that it's just the per sample loss. So basically what it means is that we are sampling the experiences where the agents makes the most mistakes, where it has the most to learn. And it's fine, and it works. So now going back to our large batch sharing algorithm, the idea is to downsample the large batch to the mini batch thanks to these quantities, so these per sample losses or TD errors. So this is quite a simple algorithm. We have tested it on the pursuit environment. So in the pursuit environment, there is a red team, there is a blue team acting on a grid world. The blue agents being the evaders and the red teams being the pursuers. And the red team is controlled by the multi-agent systems. And the goal is the goal of the game for the red agents is to catch every evaders by surrounding them. And the game ends when there is no more evaders in the game. So the LBS algorithm, the large batch sharing algorithm, has very promising results. So we have tested it on this grid world environment. We have compared it against the baseline I previously mentioned, so namely the independent DQN algorithm, the parameter sharing algorithm, and also we have tested a variant with independent DQN algorithm, but sharing one single replay buffer, and it proved to bring a substantial improvement. Of course, it is very hard to draw any conclusion from a single environment, from a test on a single environment. It is, maybe I should have said it earlier, it is a very prospective work for now. It is also a work in progress. We will have to test it on other environments to see if our algorithm performs well in practice. And also, as I said, the idea is not to learn a certain behavior given a static environment, but the goal is to adapt to a changing environment. And as far as I know, there is no classic benchmark in the multi-agent literature to where there is an environment that is changing a little bit. So we'll have to do it from scratch, and this is a lot of work. So yeah, still a lot of work to do to test our algorithms, but we think it can be a very promising work. So very short conclusion. So this is a work that belongs to the multi-agent deep reinforcement learning framework. We studied how to share effectively experiences among agents so that they could continue learning in a changing environment. We proposed the LBS algorithm, the large batch sharing algorithm, that showed good preliminary results on the pursuit environment. But of course, as I said earlier, it's a work to be pursued on changing environments with agents that are already deployed. So thanks a lot for your attention. Don't hesitate to ask any question if you have. Of course, as I said, it's a very prospective work. It's a work in progress. So if you have any feedback, it will be very welcome. Thank you very much.